This is the next chapter in what I'm calling Introduction to Biostatistics using R. We're going to start chapter 4. So let's jump to page 52. And really, probability distributions, it's the absolute backbone of statistical analysis. And in understanding how probability distributions work, how to calculate probabilities, it's absolutely crucial in describing uncertainty and variation in your data and making valid inferences in most cases. We're going to start by looking at discrete random variables, and a discrete random variable, as opposed to a continuous random variable, can only take on countable number of distinct values. Now, countable is a mathematical term that means there's a relationship with the integers. So there's distinct values. It could be infinite, but there's sort of a one-to-one mapping from the domain to the integers. And so they're typically whole numbers that arise from some sort of process. So formally, a discrete random variable x is a function that maps a sample space to the real numbers. Now, we associate probability with each outcome. So notationally, it's the probability that our random variable takes on this value x, and that's of course probability. Now, if the random variable is understood, you can leave it off and just say the probability of x, and sometimes that's capitalized, sometimes it's not. Or you could just say f of x, because usually there's a function that describes the random variable and the values it can take, and that function generates the probabilities associated with it. So f of x is also used quite a bit. But the x is the value that it can take on, not the random variable itself. Sometimes they'll put a subscript x, f of x. So some common examples, the number of heads in 3 flips of the coin, the number of students absent in class on a given day, the number of times a die lands on a 6 in 10 rolls. Those are all discrete random variables. Now, the probability distribution of a discrete random variables is some way to present two things. One, the possible values that it can take on, what values can your random variable take on, and then a corresponding probability. And that can be done in a table, it can be done with a graph or some sort of mathematical equation. Somehow, that's what we need to display or make understood. And discrete random variables all must abide by the 3 axioms of statistics. One, all probabilities must be between 0 and 1, and this is for all values that it can take on. The sample space must add to 1, so the probability that something happens is 1. And so you can think of it as the probabilities that a random variable takes on x summed over all possible x is 1. That's the sample space. And since in an experiment you can only have one or the other, you can't have both. So so the probability of mutually exclusive events is still the sum of those probabilities. And that's axiom 3 in the Kolmogorov axioms. Now, as mentioned, it can be represented in various formats, including a table listing all possible values. So here's using R to create a table. And so n is 6, and that's going to be the parameter in a binomial distribution, which we haven't discussed yet. And the x values can take on 0 to n. And we're going to row bind the values of x and then the density values associated with, which are probabilities. We're going to put that in p.dist, which stands for probability distribution. We're going to name the dimensions of it, and then we're going to print it. And it creates this table here. Okay. So the values that X can assume are 0, 1, 2, 3, 4, 5, or 6. And then we have probabilities associated with each of those outcomes. And if it satisfies the three axioms of probability or of statistics or probability, then it's a probability distribution function. And so all of these probabilities are between 0 and 1. If we were to add them, it would sum to 1. And the additivity, so the probability of mutually exclusive events, you add individual probabilities. So the probability that this random variable takes on the value 1 or 0 is you just add those probabilities. Now you can visualize these distributions. It doesn't have to be a table. And when you look at this, sometimes you don't get a good feel for, how the probabilities are grouped in a sense. So if we create a plot of X and then this density that we plotted, you can see it in here. And so the values that it can assume, and then the height of this bar is the probability of that particular event. And notice that type equals H, that stands for height. So you put in the X value and then the Y value, which is in this case probabilities, and then it creates these little bars. And this is for a binomial distribution, which we'll talk more about in a little bit. But there's other ways to create this. Well, first of all, from the graph, you can tell that it's a right skewed distribution. And most of the probability is 1 or 2. And so a graph, you can glean things quicker. There's another way to display this, and that's with a bar plot. And then it creates, you have a width and a height. And so that's what bar plot does. And so what's nice about this is the height is still the probability, but the width is 1. So the area of this rectangle is probability. So now you're really kind of thinking about it as area under the curve as probability, which will make more sense when we get to the continuous distribution. But it's just, I think it's a little bit easier. You can tell that most of the probability is, lumped between, 1 and 2. So this particular distribution can be expressed with a formula. And what the formula does, and sometimes we just call this f of x, it tells us, so assuming we have a random variable, and these are the values that it can take on, and this function tells us the probability. So if you put in x equal 1, and then 1 here, and 1 here, and 1 here, and calculate that, you're going to get precisely that height. And almost always, we're going to use some sort of function to describe, probabilities of the discrete type. Now we have what's called a cumulative distribution function, just more commonly called the CDF, and it calculates cumulative probabilities. It's the probability that a random variable takes on a value less than or equal to this script X. It's denoted with a capital F. So little case f describes the probabilities of individual values, and then capital F describes probabilities of being less than or equal to that value. Now we can plot the CDF, and notice that here P and then the distribution name, that creates cumulative distributions. It's a cumulative function. And so we're going to plot the X values, but we're also going to plot the probability, or the cumulative distribution function. And here, it's a new type, it's S, and there's actually a capital S and then a lowercase s, and then it creates step functions of different types. where it's kind of, the difference is where it goes up. Here it it went up at the integer value, and then and so it creates this. This is a cumulative distribution function. So the probability of being less than or equal to 3 is that value, whatever it is. So that's the CDF of a binomial. Now, this works well in a lot of cases and usually sufficient, but we can do better. And I'll show you what I mean. And so I created it's a user-defined function to plot the CDF of a discrete random variable. And we're not really going to go over the exact commands, but we are going to use it, and then we'll explain what it is. So discrete CDF, so you put on the values it can take, and then these are the density values of the binomial. So and so these are the individual probabilities. So that's like little f of x. That's what this function represents. Where if that d were a p, then this function would represent capital F. So you put in the values, you put in the density values, and then this function will plot the CDF. Okay, and this I like better because the values that our random variable can take on are 0, 1, 2, 3, 4, 5, or 6. So the probability that we're less than 0, I didn't say equal, less than 0 has a 0 probability. And I put that little arrow meaning that no values below 0 are accepted. But once you get to 0, this is the probability. And it's that probability until you get to the value 1. Remember, this is a CDF, and so we're plotting the values like this. And then once you get to 1, it's the probability that you're less than or equal to 1, which is you add this and then the probability that you're at 1. It's this because they're mutually exclusive events. So that's the probability. And notice that at 1.5, that number, which goes there, that's the probability that x is less than or equal to 1.5. But this is a discrete random variable, and it can't take on fractional values. So that's the same as the probability that our random variable is less than or equal to 1. So that's why it's constant until it hits the next value and then jumps up, and then it's constant and constant. And notice that once we get to 6, I drew an arrow to the right because everything past that, the probability is 1. And again, that makes sense because what's the probability that x is less than or equal to 7? Well, it can't even take on 7. The biggest number is 6. So this is the same as the probability that x is less than or equal to 6. And that's 1. I mean, because x can only take on the values 0 through 6. So that's the entire sample space. And so anything above it goes to 1. Now let's look at an example in R to find the probability distribution. And I'd highly recommend you go through this and double check the numbers and make sure you understand. But let's let our random variable be the sum of 2 rolls of a dice. Let's find the probability distribution of t. Okay. So notice that t can only take on the values 2 through 12, right? If we roll double 6 or double 1 or anything in between, and each of these values have different probabilities associated with it. And so this is just one way to find the probability distribution of t. So I'm going to use the expand grid function, and we're going to roll a die, and its values can take on 1 to 6. Die 2 can take on 1 to 6. And this expand grid lists all possible rolls. So it goes through and puts a 1 1, and then a 1 2, and then a 1 3, and then all the way down for all possible combinations. And it puts that in here. So that is this variable, die2 rolls. And you can think of it as a data frame or a matrix that has two variables. So this is die1 and this is die2. And each row represents the roll of these two dies. So notice that there's 36 rows and two columns, and as it should be. But now we want to, when it's a 1 and a 2, the sum is 2. 1 and a 2, 1 and a 1 is 2, 1 and a 2 is 3, 1 and a 4, a 1 and a 3 is 4, and etc. And so these are the possible values. And the probability of each outcome is 136, right? We're rolling two dice. And now we want to group like the values that are possible. So we would group a 1 and a 2 and a 2 and a 1 together because its possibility is 3. So the sum of those two probabilities would equal, whatever this is. Okay. Well, it's going to be 236, but we're going to do it using R1 to just understand R a little better. So what this apply function does is it takes this matrix or data frame over the rows. If it were column, that'd be a 2, and we're going to add them. So the t.dist is this vector of all possibilities. And then I'm going to create another vector with only 1 over 36 going down it. So t.prob has 36. It's a vector of 36 with 136 in each of those. Now we're going to aggregate, which means we're going to summarize over a grouping variable. So we take our t. This are the probabilities, and then we're going to group it by the possible outcomes. So it's going to group all like values and then sum these probabilities, and it's going to output this. And so that's it. That's a probability distribution of rolling two die. There's a 0.02 probability of a 2. There's a 0.111 of rolling a 9, and that's it. That we could call that f of t, or the probability. Oh, that's a t, not an x. Equals some value. That's what these represent. We can plot them. So with our new table that we just created, let's bar plot it. And this is it. And this is a graph of the probabilities. And as one would expect, the probability of a 7 has the highest probability. And then, of course, 2 and 12 have the lowest probabilities of outcome. Let's plot the CDF for this. So with this table that we created, let's use my user-defined function, discrete CDF, and plot it. And this is the outcome. So each dot on this line is that's F, capital F of t. So it's the probability that our random variable is less than or equal to that value. Notice it starts at the left limit is 0 and the right limit goes to 1. And it's a step function going up. Now, discrete random variables, if it has a distribution, then it more than likely it has a mean and has a variance. And I say more than likely because there's some weird cases where it is a true random variable, has a distribution, but the mean and the variance don't exist. But usually they do. And actually we'll just leave it at that. And so the mean of a population is you take the values that it can assume. So in this example, little x represents 2, 3, 4, all the way to 12. And then this is the probability associated with with obtaining that value. And then those are summed, and that's the population mean. Now the variance, as we described earlier, it's the average square distance from the mean. So you take all possible values, these 2 through 12, subtract the mean, which is here, square it, so that's the square distance from the mean, and then times its respective probability. And notice that I probably should have put a lowercase p there, right? Which that's what I've been using for probability. And this is it. This is the variance. That's how you calculate it. Now, in some courses, we go through the math to prove that there's a shortcut formula, which is this. So you take each value squared times its respective probability, summed over all possible values, and then after you complete that sum, you subtract the mean squared. That's also equal to the population variance. Oh, why am I saying population variance? Well, this random variable t, its entire population are the values of 2 through 12. That's it. It's the population. So these are population mean and population variances. So let's find the sum, or this is, of course, a continued example where we're going to roll 2 die. T, of course, is the sum of the outcome, and let's find the mean and the variance of our random variable t. So if we use the apply function over this matrix, over by row, and we use product, so that takes the value times its probability, and then value times probability for each row of this, because we used the 1 there. And then we sum it, and we get 7, which we know to be the mean of rolling 2 die. You could do it like this. If in the table there's an outcome, so that's the values 2 through 12, and then there's a probability associated with each outcome. Remember, those are vectors of the same length, and when we multiply them together, that's Hadamard's product. So you multiply it component-wise. So there's a vector now of outcome times probability, and we need to sum it, and we get the same thing. Now, to calculate the variance, remember this is population variance, not sample variance. So we're going to take our probability table that has outcome in one column and probability in the next. We're going to do something by row, and notice this parenthesis goes to that. So it does all of this first and then subtracts the mean squared. So it takes the value it can take on squared and then times the probability of assuming that value. Then it sums it, and then it takes the mean squared. So that we just used this formula. Of course, you could do it with a more using the variable names. Table outcome squared, so that's the x squareds, times the probability of assuming that, sum it, minus the mean, 5.8. I just think that the apply function is so powerful, so I'm going to use it over and over. All right, well, we're on the next section, which is binomial distributions, and we're 23 minutes. So I'll stop here, and we'll start up in the next video.